The principle can be changed in the following way. We create a vacuum and, in order to balance the charge, there are perhaps two foils. One is the target, which produces, and the other which balances. Of course, it would be ideal not to have to make use of foils, but rather to suspend the atoms in mid-air, by making use of a gaseous medium instead of a vacuum. It is possible to separate the products of the complete fusion reaction from the calcium-48 beam. This would increase the distance between the atoms, and each time they collide with the atoms in the gas that is in the separator, they would interact many times, resulting in the ionic charge of the reaction product having some average value while corresponding to the product velocity. Increased speed means increased charge, and the lower the speed, the lower the charge will be. This is a statistical process with many interactions. It is possible to show later that 10 interactions are enough. After only 10 interactions, it already takes on an equilibrium charge. This equilibrium charge is shown here. The one on the left is substantially smaller than the other. It is narrower and has only one ionic charge. The nucleus of thorium-217, which is obtained here, does not have such a spectrum, but has a charge of 6.15 plus minus 0.2, which is very narrow. Then we have to inject into the gas the recoil nuclei. We also need to choose the optimum gas because, on the one hand, we need to have enough atoms so that it can statistically interact with everything, and on the other hand, it would be good if there are not very many atoms because they lose their energy during this interaction. It turns out that the optimum gas is 0.7 torr to 1 torr, approximately 1/1000 of the atmosphere. We're filling this volume with hydrogen. This means that the recoil nucleus flies into the volume of hydrogen. Its charge depends little on z, but very much depends on the speed, which is expressed here in Bohr speeds. And then the magnetic rigidity will be proportional to the mass by the speed and divided by the charge. Neon has a charge of 20 and Z equals 6. 3 times the charge. Now we can separate evaporation residue from projectiles in a magnetic field. Therefore, you can create a system like this. A beam enters, and this is the target. The target is not in a vacuum, but it is necessary to make a rotating window, like the rotating target. It passes through the window, enters the volume of hydrogen, and hits the target. Both the beam and the recoil nucleus emerge from the target. The beam has a charge of 20, so it is strongly deflected in a magnetic field. The recoil nucleus has a charge of 6, so it is weakly deflected. It has a higher magnetic rigidity, and in principle, we can put a focusing system here and assemble it at a focal plane. This distance from here to here is 4 meters. The nucleus covers this distance in 1 microsecond. Therefore, if the reaction product that originated here has a half-life of more than 1 microsecond, we will certainly see it here. If less, then we will not see it. But the speed of the system is already only 1 microsecond, and, as you saw earlier, its efficiency is about 30 to 40%. This is a kinematic separator. This is the entrance to the separator, and here is the target. This is the exit where the detector is located. Let's talk a little about the detector. Having flown this distance of 4 meters, the recoil nucleus passes 2 thin counters, each generating either a start or stop signal. Since the distance between them is known, about 6 centimeters, we can determine the approximate speed of the recoil nucleus. It flies through the thin detectors, moves on, and rests against the front detector, and slows down. The front detector is actually called a strip detector because it consists of individual strips, like piano keys. Each strip has longitudinal position sensitivity. The number of the strip will be the x-coordinate, and the position of this strip will be the y-coordinate. The recoil nucleus flies through the detectors, with the time of flight indicated by the system, and continues on until reaching the stop signal. The coordinates of this signal are immediately clear. And then we wait for the decay. If this particle underwent spontaneous fission, then there would be two fragments. One fragment will go inside the strip detector, we will see it, and another fragment will move out of the strip detector. If it has experienced alpha decay, then the alpha particle will go either inward or in the opposite direction. In order not to lose those which go in the opposite direction, the front detector is surrounded by side detectors, so that the entire array has the shape of a box with an open front wall. We measure energy by the time of flight, and we determine the position where it left off. Then, if we see any alpha particles, first, second, or third, we measure their energy and also their position. We measure the position every time. If all of these decays belong to the same nucleus, then all of the decays will occur from the same position on the detector. Only in this way can we establish a genetic link. When the nucleus has stopped decaying, the first decay is the mother, the second is the daughter, the third decay is the granddaughter, and the fourth is the great-granddaughter. That is, we can see the entire radioactive family. Why am I saying this? Because in fact, the theory does not just say whether it will or will not live, for either a long or for a short time. The theory predicts how they will decay, how long they will decay, and how long this chain will be, which we refer to as the decay chain. Now about the characteristics of the separator. The figure shows how the charge of an ion depends on its velocity. And here we see a dark smudge representing the nuclei that passed through the separator and hit the detector. Here we see these famous strips. This is the size of recoils at the target. This was the size of the evaporation residues at the focal plane of the separator. And here it became different. We can determine its vertical position, and it is approximately 6 square millimeters, while the whole detector is 4,800 square millimeters, approximately 50 square centimeters. You can clearly see that if the first particle reaches this position, it is the mother. If the other particle is not the daughter of this mother particle, it will not reach this position. The probability of the daughter particle reaching this position is 1/800, meaning that the granddaughter particle will definitely reach this position with a chance of 1/800 times 2. Therefore, if they are really genetically related, they will all come from this strip, the first, the second, and the third. And in this way, we can establish a genetic link between the decays. And this is the efficiency of this separator, how it behaves for different combinations of targets and ions. We are located somewhere in this area. Element 114 will have approximately 40% efficiency. It is not bad.